Hello everyone, this is Patrick from Security and Privacy Academy, and today we are talking about secure multi-party computation and the Millionaires problem. So let's jump into it. The idea behind secure multi-party computation is to allow shared computation on secret data without revealing any secret data to any of the participants of the computation. So another way to look at this, for example, is a treasure map, which is divided into 4 separate parts, so that no party alone can find the treasure, but they have like all 4 treasure hunters can find the treasure only together. In this video, we focus on the millionaires problem, which is stated as follows. 2 millionaires want to know who is richer, who's wealthier, but they do not want to reveal their wealth to each other. Another way of stating the problem is that 2 employees we have here, like Alice and Bob, they want to know who makes more without revealing the salaries. For example, Alice wants to know whether she's underpaid, and so they can use secure multi-party computation, or SMPC, to find out who makes more. The caveat here that this algorithm only works on natural numbers, but luckily for Alice and Bob, both make natural number salaries between 0 and n. The algorithm now works as follows. Now please bear with me, I will give an example with actual numbers later, but first I will explain the algorithm only in an abstract way. First, Alice chooses an X at random and encrypts it with Bob's public key, which is denoted here as E, the encryption key, which is the public key in a public-private key infrastructure. And the resulting ciphertext, C, is, the resulting ciphertext is called C. Then next she subtracts her salary from C and sends the result, D, to Bob. Alice now knows X, and of course her salary, but she actually doesn't need that from here on out. And Bob only knows the value. I mean, he knows his salary, of course, and the only other thing he knows is the value for D. Now it's Bob's turn, and he calculates a series yi by decrypting D. B is his decryption key, plus the natural number I, which iterates from 0 to n. That's why it has to be bounded by an n. From the series yi, Bob then calculates the series zi by applying some function f, which is known to both Bob and Alice. So this is a public function. And it could be basically any function. We will see in the example later that we use the function, for example, x divided by 3. Bob then adds his salary to the series, which is a bit of a simplification. He doesn't really add his salary to the series. He just he doesn't really adds the amount of his salary to the series, but he changes the values of the series following the position given by his salary. So you can see here, if his salary, for example, is 4, he increases the values following the 4th value by 1. And this will be much clearer in the example that follows after I've completed the algorithm. He proceeds to send Zi to Alice, who now obviously also knows this series. Alice now concludes the process by also applying the shared function f to her original number x she chose in the first step, and if f of x is in Zi, then Alice earns more. But if f of x plus 1 is in Zi, then Bob earns more. This is the binary choice, or the binary decision she derives. That concludes the algorithm, but as promised, let's look at an example with concrete numbers. So let's say Alice earns 8, let's say $1,000, and Bob earns 5. And the highest salary, so that we have enough space on the slides, is 10. So they know this beforehand. They know beforehand the lowest amount can be 0, let's say, but the highest amount can be 10 let's say $1,000. So the encryption function is very bad, obviously, but it's just to make things a bit easier, and it just divides the number by 2, and so decrypting obviously means that you just have to multiply the number by 2. The shared function f is also a basic function and is just x divided by 3. So let's start the algorithm. Alice chooses an x equals 25, therefore the encryption, so c equals 12.5, which is half of 25. She then subtracts her salary, and the resulting number, 4.5, is sent to Bob. So in addition to everything she knew before, she now also knows her chosen x, which is 25, and obviously she knows the value for d, and so does Bob. So Bob now has to calculate two series. First, he calculates the series yi, which is the decryption of the value d, which is 4.5, plus the values for I, which are 1, 2, 3, 4, and so on until 10. The result is displayed here. And note that Alice's value for x, which is 25, is also within the series. That's always the case. Obviously, Bob doesn't know where, otherwise he could calculate Alice's salary, but it is within the series. So next he calculates zi, which is the application of the function f, which just divides a number by 3. So the result is this new series here. Now the actual, let's say, complicated part begins. It's not really that complicated, but it's a bit counterintuitive. Now Bob looks for the 6th value of the series. Why the 6th? His salary is 5, and we begin our series with 0. So he looks for the 6th. If we say like 3 is the first, obviously it's the 0th position, but if we say okay, it's the first position, then he looks at the 6th position and increases the subsequent values by 1. And the result looks like this. You can see in bold the values which were increased by 1. So the 8 here used to be 7, and the 8.67 used to be 7.67. So all the values that follow the position of his salary plus 1, since we start with 0, are increased by 1. Now obviously in this very easy series it's really easy to see where the gap is, but you can imagine a more complicated position where this is not so easy to see. He sends the series to Alice, as we know. Now Alice's job is now quite simple. She just calculates the two values, 25 divided by 3 and 25 divided by 3 plus 1, and checks which one is in the series. So we have the series here. She calculates the two values, and she checks which one is in the series. Apparently f of x plus 1 is in the series, which is 9.33. And if you remember, if fx plus 1 is in the series, that means Alice earns more. It is worth noting that only Alice knows this. Bob is unaware of the result if Alice doesn't tell him. So she knows who makes more, he really doesn't. So in order to make this process work for him as well, they would have to repeat the process with Bob being the initiator. Okay, this has been a description of the algorithm to solve the Millionaires problem using secure multi-party computation. I will definitely do a video on secure circuit evaluation sometime in the future, which is also a very fascinating application of secure multi-party computation. But for now, I conclude today's video. Thanks for watching. Tell me in the comments which topics you would like me to cover next. Like the video, subscribe to the channel, and see you in the next video.